series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. Today's talk is by Professor Parthajit Mohapatra, and he will be speaking on short packet communication under random arrival of data. Professor Parthajit Mohapatra obtained his PhD degree in ECE from IISc Bangalore in 2015. He was working as a postdoc research fellow at iTrust Center for Research in Cybersecurity at Singapore University of Technology and Design from March 2015 to July 2016. He was working as an assistant professor at GS Sanyal School of Telecommunications at IIT Kharagpur from August 2016 to July 2018. He was also a visiting faculty at Information and Communication Engineering Department, Daegu Gyeongbuk Institute of Technology and Design, South Korea. Since July 2018, he is working as an assistant professor at the Department of Electrical Engineering, IIT Tirupati. His research interests are primarily in the area of physical layer secrecy, short packet communication, union of physical and network layer techniques. Before we move on to the talk, we would like to request the online audience to subscribe to our Google group for information on future talks. You can also visit our website for more information. I'll be pasting the links in the chat box. Please do check. Finally, we would request the audience to please keep your microphones on silent for the duration of the talk, except while asking questions. And for questions, you may unmute yourself and ask Professor Parthajit directly. Over to you, Professor Parthajit.
Yeah, thank you, Munmun. So it's always pleasure to give a talk at IISc. No doubt it would have been more pleasure if I would have given physically, but due to some unforeseen situation, I could not come there, as I've told earlier. But anyway, I'll move on to the talk. So this talk is primarily focused on my PhD student work, and like I'll kind of give you a little bit of a big picture about it, but then I'll kind of move into what problem we are trying to address. So initially we are having some of the results. That is what I'm trying to present today. And also I think my PhD student Dheeraj is also here, I think. So I'll not go into much of these details, like, but particularly I feel very excited when I see how the wireless communication has evolved over time from cellular network to now we're talking about 5G, and in academics already we started talking about 6G. But quickly I move into some of the areas that we are currently focusing on our group. When I was at IISc, I started working on physical layer secrecy with Professor Chandra R. Murthy. Then I still keep on working on physical layer secrecy, and currently the focus have been little different. We are also looking into the short packet communication with secrecy and without secrecy constraint. Initially, I thought I'll kind of give talks in secret with and without secrecy, but then I thought of giving only with respect to the talk without secrecy. Then also we have been also doing some of the collaborative efforts with Linköping University, where we are trying to unify some of the aspect of physical layer and network layer. So this talk is kind of between short packet communication, although I'm talking about short packet communication, but it kind of also tries to see what is the benefits if you get, if you try to unify physical layer and network layer. I hope my voice is audible. Because in online some of the time we don't know, we don't get the feedback immediately.
I can hear you well, Parthajit.
Okay, thank you, sir. Yeah. So currently, like I think many of you already aware of that. Like in 5G, we are having two important modes of communication. One mode we are calling it as massive machine type communication. The other one is ultra reliable low latency communication. And if you look into many of the emerging scenario in particularly in use case scenario of 5G, like one of them is M2M communication or machine to machine communication, or in case of the sensors also, if you look into IoT scenario, generally the traffic that we see, that is actually in the form of short packets. Another, not only like we, particularly if you look into this communication, particularly in uRLLC. There we have two kind of requirements. One is actually reliability, the other is latency. Uh, then an important question arises, when you want to achieve both, can you achieve both simultaneously, or is there any cost associated with it? And in particular, if you move into the network architecture, what we see now, it is going to be more and more decentralized in nature or distributed in nature. And once we look into distributed scenario, interference is going to be unavoidable. Then if one asks, what is the impact of interference on the latency of communication, there are very few works actually which actually talk about it. Because most of the information theory work, if you see, like maybe starting from the era of 1980s or till now, most of the work particularly focus on reliability aspect or the capacity aspect, or how much data rate we can get. That is what it primarily focus. But in current communication scenario, or more particularly for the future communication scenario, if one looks, only looking into reliability or the rate may not be enough. What we may have to also look, what happens to the latency. So toward the end of my talk, I'll come to particularly these latency aspects. Let's keep moving. So currently, like if I look into the literature, particularly most of the literature, if I look, there are two important metrics that is being used. One is basically capacity or capacity region if you go into multi-user scenario. The other one is outage probability. Then an important question comes whether this kind of metrics can you use for short packet communication, where latency and these kind of factors are also of important aspect. And if I look into this capacity characterization or this outage probability kind of performance analysis, one of the underlying assumption is large packet length. So then when you want to have low latency communication, particularly in short packet communication, where reliability is also a important criteria, it's not an easy task, particularly when interference is also there. Not only that, if I look into our communication scenarios, their data arrival is also random in nature. We may not always have data available to transmit. If I look into information theoretical literature, one of the standard assumption involves is that user always have data to send. But in many real world scenario like IoT or M2M scenario, if you look, we may not always have data there to send. Then how do I take care of all these aspects? Can I come up with some mathematical framework which can try to capture all this? And if you are able to capture, then it may also allow us to explore what is the impact of interference on some of the performance metric like latency. So the one of the major objective kind of that we are having, like I'll not say like we are able to answer it fully, but this is kind of a bigger question. Like, can you come up with a mathematical framework for particularly for short packet communication, which takes account of reliability as well as latency associated with the communication? Now let me goes back to like one of the work of David Say, which I was reading some time back, where in the introduction, what is mentioned is like Longback Gallagher has pointed that like information theory provides very accurate model for interference or noise or in general whatever the uncertainty associated with the physical medium, but it generally doesn't capture the random arrival of data or kind of the bursty nature of the sources. Now if I look into the network actually generally provides very good mathematical tool, a lot of models which can actually try to capture the random arrival of data, bursty or the burstiness of the sources, and also it has kind of look into latency and other aspect. Now the question comes if we unify both, can you get best of both the world? That is one of the natural question comes into mind, and that is what we try to do. Something like that we try to do in this work. Now, as I'm mentioning, like the physical layer can provide very good models. Even physical layer can provide also secrecy, reliability jointly. But secrecy part I'm not discussing in this talk. Uh, uh, but one of the assumptions that general information theoretic results pose is that you always have data to send. Now, if I look into network layer, it can provide a very good model to capture the bursty nature of the data. And also we can, many of the quality of service metric which were of interest, particularly for the emerging communication scenario, like delay or age of information, that can be useful. So this kind of motivates us to unify these two words. And but if I look into the literature, if you ask like, I'll come back toward the end what I mean by this interplay between security, reliability, and delay. Although I'm not going to discuss this much in this talk, but toward the end I'll give a little bit of idea. So if one look into the literature, very few literature actually talk about what happens to the delay aspect, particularly in physical layer secrecy or information theoretic secrecy. If you want to see, if I guarantee security, but what is happening to the latency aspect? What is happening to the delay aspect? Can I answer some of these questions? So there are very few works, not much work is done in this regard. And that is where like, but what I believe is for the future networks, what is going to be very important is to come up with an integrated mathematical framework, which can capture some of the important aspects like rate, reliability that we talk in general from physical layer point of view, whereas some other aspect like maybe throughput or latency, we talk from the network level perspective. And this talk is going to mainly focus on the first part. The second part, although we are having some of the results, I am not presenting in interest of time. And this is the kind of the bigger question we are having. And in this talk, I'm going to present some of our initial results in this direction. Okay, so now I'm moving to the problem statement, but if there is any question, I'll be also happy to answer at this point of time. Okay, so now, as I mentioned, particularly in many of these emerging communication scenario, the traffic which is generated, that is kind of in the form of short packet, and also the source may not always have data to transmit, or rather the arrival of data at the source is random in nature. Then many of the work, if one sees in particularly in short packet communication or maybe finite block length information theory as application to wireless communication, they use some of this packet length as a kind of a measure as a physical layer latency. But one of the problem with this kind of thing is it doesn't take account of the queuing delay. So how much the packet is going to sit in the queue, that is kind of not taken into account. So only looking to the packet length may not solve the problem related to the latency. So that is where it is very important to look into account what is happening to the queuing delay. At the same time, one also has to see how much, like what is the my length of the packet. So both things need to be taken into account. At the same time, if I look into particularly interference mitigation techniques, for example, as I progress, I'll be kind of going to little more details. For example, treating interference as noise is one of the very conventional scheme that is being used. I think today also most of the system uses still treating interference as noise. So similarly, there are some other sophisticated schemes are there like successive interference cancellation or joint decoding. Now, if someone asks what is the performance of this when you are using short packet, That is not very well understood from the existing literature. Although there are some results are there, but still there are a lot of scope is there in this direction. So in this direction also, we try to address some of these aspects that I'll kind of mention as I progress. So finally, the one of the major objective is to try to explore what kind of interplay exists between reliability, or you may say the throughput, latency, and the packet length, but in interference limited scenario. So that is what we are trying to address in this work. So I'll quickly move to the system model. So this is a very kind of a bit information theoretic model, which is kind of studied very well in information theory. But with queues, generally it is not studied that much, to my knowledge. So it's known as a G interference channel, where in this case, there is a transmitter 1 which has a queue which stores the incoming packets. Similarly, the transmitter 2 also has a queue which stores some of the incoming packets. So what we are assuming is that the packets at both the transmitter kind of arrive independent of each other, and with some probabilities lambda 1 and lambda 2. Whereas the transmitter 1 has a message packet intended to receiver 1. Similarly, transmitter 2 has a packet intended to receiver 2. But in this work, we are assuming that there is no interference from transmitter 1 to receiver 2. Later on, I'll give little more remarks like how our results can be generalized even for the two-user interference channel, where actually both the users can cause interference. But I'll not go into all the details there, but I'll just kind of highlight how this result can be extended to the two-user interference channel. But let's focus on this model, which has some of the beauties mainly from the, like one of the angle is from the information, sorry, mainly from the mathematical tractability. And in practice also, it can model some of the scenarios. And in this case, the assumption is like the transmitter sends a packet whenever it has a packet to send. Otherwise, it will remain silent. If it doesn't have any packet to send, it will just remain silent. But whenever it has a packet to send, it will send. I'll come to some of the random message thing a little bit as I progress. But currently, like transmitter sends a packet whenever it has a packet to send. And whereas I'll use this QI to denote the length of the queue. Now also we have a physical layer model. So whatever I talked about, that is mainly the network layer model. Now whatever also we have a physical layer model, which kinds of look into what kind of underlying physical model is there. For example, in this case, we have taken it to be relay fading. That's all the channels are drawn from a relay fading distributions, and they are independent of each other. Then this rate, whatever we have defined, it's slightly defined a little different way that we see in information theory. So here Ki basically corresponds to the number of information bits that I have, and n is the packet length. So one may assume that n minus Ki is basically my kind of a metadata or some kind of a control bits. So in general, like I'll not go into the much details, but for short packet communication, how much data bits we are having, or in particular how much control bits or whatever the other metadata I'm having, that actually plays a very significant role. But when you look into asymptotic regime, when n is very, very large, then actually the size of the metadata is kind of very negligible. So that is why if one looks into Shannon derivations, channel coding theorem derivation, this notion of this control bits or metadata doesn't come into picture because n is very, very large. So that is kind of neglected. But once we are moving into short packet communication, we cannot ignore that size of the metadata. So that is something one has to be taken care. Now I'll come to the approach. So in this case, as I mentioned, like in this case, the transmitter may not always have data to send, or rather the data arrival at the source is random in nature. So we use some metric known as stability region that I'll kind of define. I'll not go into all the details, but I'll kind of define what it is. Then I'll I'll come to this point, like how do we try to evaluate the stability region? And there are actually some interesting connection to the capacity region that also I have not included in this talk due to interest of time. But yes, there are a lot of there are very few works which try to kind of see what is the connection between stability region and capacity region. And the major thing what comes is like we need to determine whether when I transmit a packet, whether it is going to be decoded successfully at the receiver or not. And that basically we get it using the framework of finite block length information theory. And once we characterize the stability region, then that actually helps us to explore the impact of interference on latency of communication. So this is kind of a very overall idea. So as I progress, I think it will be more clear. And if there is any question, I'll be, please feel free to interrupt me.
Sir, I have a question.
Yeah.
So the short packet message size, is it deterministic or is it random here?
No. Currently, the packet length is deterministic.
Okay. And
only, yeah,
for the arrival process, is it a Poisson? Like, what is the model?
Yeah. So okay, I'll come back to it a little bit later also, but maybe I can just say a few things here. So currently, for some part of the results, we don't need to assume kind of it has to be from a Poisson process or any particular distribution. So it has to be from a stationary distributions. But for some other part of result, we need some assumptions. Yeah. So as I progress, maybe I'll point that. Yeah.
Okay. Thank you.
Okay. Yeah. Yeah. There is, I think, one more question.
I had a question about the metadata. You mentioned metadata. So is that the metadata at the MAC or physical layer, or is it the network and the higher layer metadata also, or the controller and signaling packet?
So I think it is as a whole, whatever it is going from the transmitter to receiver one. So when I'm saying that I have some data, after that there are some other data coming in, particularly at that physical layer. So that is kind of my meaning here. Yeah. But across the layers, whatever communication may be happening, that it may not take into account. Yeah. So currently it is a bit abstract. What I say is here, we are not exactly defining what it is. Yeah, so is that fine or?
Oh, sorry, please go ahead. Thanks.
Yeah,
that clarifies.
Okay. Yeah, thank you. Okay, so now coming to this, so this is not that only work which have looked into finite block length information theory and some kind of unification of networks. There are some of the works in the literature which are there, like which look into particularly what is the benefits of NOMA in reducing queuing delay. Like I think we talk about non-orthogonal multiple SS quite a lot these days, but one of the major question comes when you are using short packet communication, what is the benefit you get in reducing the queuing delay? So that is what I think this work tries to address. Then there are some other works which look into some kind of this stability conditions for this multiple SS with and with relay kind of channel under finite block length constraint. But currently what we have seen is that when interference is there, particularly that part has kind of remained ignored. And that is actually like kind of motivated us to look into this angle. So similarly, like if I want to look into the stability region, so the stability region has also been looked into two-vision interference channel, but there it doesn't take into the account that the packet has to be of finite length. So it doesn't basically consider that aspect. The length of the packet, it doesn't take into account. But stability region for interference channel has been looked by this work. Okay, so currently I'm presenting like one of our, so this is the extended version of the conference work which appeared, which was presented in Globecom. And so in this work, basically, we can characterize the stability regions for the G interference channel. And then I'll come back like to the point, like why the probability of successful decoding determining is very important. And that is where the framework of finite block length information theory helps. Then again, we also kind of explore what is the impact of interference on latency. And when you look into a latency, again, we look into two kind of metric. One is delay and another is edge of information. I'll come back as I progress in the talk. But I think one of my major part of the talk will be kind of focused on this stability region and the probability of successful decoding. So toward the end, I'll give some of the results related to the impact of interference on latency. Now, stability region is generally like when you look into multi-user scenario. So there, what we try to define something called stability region, which is defined as the set of all reliable rates, so that all queues in the system are stable. So I'm not going to all the mathematical definitions here, but roughly what it means actually, I'll maybe as I progress, I'll give some example that will make it a bit more clear. But interesting thing is that it is people kind of consider it as a analogous to capacity region in network information theory or multi-user information theory. Like we define the capacity region where any points you take in the capacity region, it's going to be achievable. Similarly, now once you have a stability region, any point you take inside the stability region, that for that 2 points, the queues are going to be, all the queues in the system are going to be stable. But the problem is like when you try to characterize the stability region for multi-user scenario is again a difficult problem. It's not a easy task. One of the problem arises because of the interaction among the queues, because whether a queue has a packet to send or not, it's affect the performance. Like in conventional information theory, this kind of scenario doesn't arise because if there is interference, it is always going to be there. But when I'm looking into this random variable scenario, then the performance of one system depends on whether what is the status of the other queues. So what happens? There is a coupling or interaction is going on between the queues. Then there are different techniques are there. I'm not a full expert in network. I have learned some of the techniques, some other things, mainly from my collaborator Nicholas. Particularly like one of the technique they use, they call it as stochastic dominance, which try to overcome this coupling among the queues. But again, there the problem happens. This stochastic dominance technique generally doesn't scale up. Like for 2 to 3 users, you may be able to use, but if you again want to extend beyond 2 to 3 users, again, it's a difficult problem. So that is where, in a way, it is analogous. One way, like if you look into the capacity region for most of the many communication models, except for very few models, the capacity region is known. Whereas similarly for the stability region, if you see again, the stability region is known for some very specific models. Again, if you want to kind of generalize it, it's not easy. Or finding some of the closed form expression may be difficult. You can find some of the thing, but you may not be able to find a closed form expression. So now I'll just highlight first result of our work, where the stability region of the two-user interference channel is basically given by this equation. Here, basically, this lambda 1, lambda 2 are basically the arrival probability. And so in this case, this particular term, this probability of di superscript tau, So that basically kind of denotes what is the success probability at receiver I when a packet is transmitted by transmitter I given a set of active transmitters. So, for example, when I'm saying this probability of D1 superscript 1, 2, so that basically denotes what is the success probability at receiver 1 when both the transmitter 1 and 2 are active. So this is how my stability region is given. And what actually one can prove, that actually proved not here in some of the other paper, I think I'm not mentioned here. This is going to be a necessary and sufficient condition. That is something interesting here. That is going to be a necessary and sufficient condition. But the question comes, what will be this success probability? How do I determine it? Now, there are works in some of the cases, they assume some of these values. But in suppose I want to really see if I have some different kind of decoding schemes, and at the physical layer again we have different kind of parameters which again influence all the success probability. So then how all these things basically can affect my stability region? So I'll make it a little more clear as I progress. But before that, let's see how this stability region may look like. So that is what whatever result I'm presenting here, it is actually irrespective of any kind of scheme that you use. In a way, it is general because I'm not assuming any particular scheme. But the problem is, if I want to evaluate the stability region, then I need to know what are these probabilities. Without knowing these probabilities, I cannot evaluate it. So, so this is kind of one kind of the plot how it may look like. So, so one can always argue that when I don't have any packet to, sorry, like when the transmitter 2 doesn't have any packet to send, so then this is always going to be higher compared to the other point. So the stability region will finally look like this. And any point I take within this stability region, for that my systems is going to be always stable. Now the question comes is, how do we evaluate these probabilities? And for that, what we do is we look into this finite block length information theory. So I'll just give a very brief idea about the proof before I move into that detail. Now, I want to calculate. So again, here we use this for the stability condition, this Lyons criteria. And so particularly if I want to see what is my service probability, it depends on the status of the second user, whether second user has a packet to send or not. So based on that, my service probability is basically determined. So in this case, basically I have a packet to send. So that is why the probability of, when I determine the probability of success, it has to take the interference into account. But when I'm not having any packet to send, then the probability of successful decoding is basically determined by only by a packet by the transmitter 1. But in this receiver 2 doesn't experience interference. So that is where some of the this service rate is given by this equation. And the good thing about this model is that the queues are now decoupled. Once I know what is this probability of that transmitter 2 has a packet to send, once I know that, basically I can evaluate the service probability. So, but for interference channel, you cannot directly do it. So that is why again you have to modify some of the things, and that is where the queues become coupled, and the analysis become not very difficult, but you have to use stochastic dominance. So in this case, without using stochastic dominance technique, you can find the stability region because queues are kind of decoupled in this case. And then you can determine this probability or the probability that the packet length is greater than 0. And once we have this, we can find the, I've not done all the calculation here, these calculations are not very difficult, then one can find this expression. So now I'll slowly move into some of the other part where basically like we kind of discuss some of the interference schemes. And in interest of time, I'll kind of discuss one of the schemes. Then I'll move into the result part. So particularly, one of the very conventional scheme is treating interference as noise. It has low complexity, and it is also kind of has good robustness to channel uncertainty in comparison to some of the other schemes, like uh, for example, successive interference cancellation or joint decoding, which generally requires more channel knowledge. And but when you try to extend the results from particularly finite block length result from point-to-point scenario to multi-user scenario, one has to be careful because this may cause non-Gaussian interference, because many of the finite block length results the achievable results are not based on the assumption that the code words are drawn from a Gaussian distribution. So this is where we okay, I'll come back. Like this is the so basically, like when I try to evaluate the stability region, I'll just go back to one slide here. I need to determine this various probabilities, and these probabilities are basically depending on the status of the queues. So basically, based on the status of the queues, we determine the various probabilities. And I'm not going to all the mathematics here. So I'll just give a very high level idea. So in this case, the transmitter one is basically sending a non-Gaussian signaling. So basically, it is where the code words are distributed over a cell, but transmitter two uses a Gaussian signaling. If I don't use, then the model will reduce to a non-Gaussian point-to-point channel. Once it reduced to a non-Gaussian point-to-point channel, I cannot invoke the results from the paper from this paper by the Poliansky. So that result I cannot invoke. So that is where transmitter 2 sends a Gaussian signaling, but transmitter 1 sends a non-Gaussian signaling. The reason of choosing non-Gaussian signaling is basically it gives you a little more, or it's a somewhat more tighter result compared to Gaussian signaling. So now, because of the mathematical tractability, we have to sacrifice in terms of some of the rate or whatever. And finally, like we try to kind of average this instantaneous error over the different channel relation, then we try to get the result. So this part I'm not presenting here. And similarly, one can obtain the results for the receiver too, because I need to determine the success probability for both the cases. But for this case, we realize the result from this what? Okay. So how much time I'm having? Like
20 minutes. Sir.
Okay. Yeah. So now, like another very promising scheme is basically the joint decoding scheme, where generally message of transmitters are decoded simultaneously at the receiver. And this has been studied very extensively under the assumption of non-asymptotic kind of scenario. But at finite block length, what is the benefit we can get? Also in terms of delay or latency, that is something not well explored. So in this case, I'm not going to all the details, but if I look into the G channel model, so then this transmitter 1, transmitter 2, and receiver 1 form a MEC channel. And in this case, again, this I'm assuming that both the transmitters are active or they are sending the data. So then they form a MEC channel. And then what I can do is already the finite block length results are exist for the MEC channel, that I can actually use it. So our main contribution here is to mainly to derive the average error probability for the relay fading scenario, which was not existing in the literature before. So some of the works have considered, but they have not provided the closed form expression. So that is what we try to provide here, a closed form expression, or I should say correctly, a approximate closed form expression Then I'm coming to the last scheme, which is successive interference cancellation scheme, which is also another prominent scheme. But in this case, what we assume is that both the transmitters kind of using again Gaussian signaling. So we have to be again, like we choose them carefully so that we have the mathematical tractability. And again, in this case, for the SIC case, if there is an error in the stage 1, it can also affect the error in the stage 2. So that also needs to be taken into account. So we kind of take error in both the stages when you try to derive the expressions. In interest of time, I have not presented these results. So before I move into some of the other results, so I just thought of showing some other results in this work. In the model, what I was having is whenever the transmitter 2 has a packet to send, it always transmit. So one natural question comes is if I transmit with some probability or will do some kind of a random access, can it improve the stability region? Because other user is experiencing interference, can it improves it? And what interestingly we saw in this work is that the stability region with random access is going to be a sub-region without random access. So basically, in terms of stability region, transmitter 2 should always transmit, like whenever it has a packet to send. So that is what we kind of shown, and it was somewhat interesting to us because we expected that initially it may enlarge the region, but it doesn't help. But there are some other cases I'm not mentioning here. Maybe if time permits, I'll go into that. So let's look into the latency aspect, then I'll move into the result part. Now, once I look into the stability region or the stable throughput, again, it doesn't give me any information about the delay or latency. Now, when I'm looking into latency aspect, there are two important aspects. One is basically the queuing delay, which generally, one generally we call it the delay, which generally have a queuing delay and as well as a transmission delay. And the other metric now popularly that I think many of you may be already aware, age of information, which kind of capture the freshness of information. So I'm not going into all the details like how it has been defined or all these things, but these are the expression that we use from the existing work. But in this case, I just want to mention like for the age of information, we need to assume particular some of the more like assumption on the arrivals, where the arrival has to be Bernoulli and the service time should be geometrically distributed. Then only this age of information expression will be valid, otherwise not. Whereas the stability region expression is somewhat more generic. It can be applicable to many scenarios, whereas one has to be careful when one has to apply the age of information expression. That is not applicable always. And also we need to have this service probability that comes from the stability region. So when I'm evaluating this delay or the age of information, it not only depends on my arrival rate at the transmitter 1, it also depending on the service rate, this mu1 of transmitter 1 and receiver 1. And that actually again depends on the arrival rate of the transmitter 2. But here one is to ensure that when I'm taking this lambda and lambda 2, both should be part of the stability region. Otherwise it doesn't, otherwise the queue will blow up. So I'll now start going to some of the result part. So now the first result is basically on the stability region. So what I've done in this case is I've only focused on the scenario, particularly like, okay, in this scenario, I think I have two results. One is the case where the interferent link, I have only, if you remember, like it's a G channel, it has one interfering link from transmitter 2 to receiver 1. So what I assume is that this interference link is kind of less stronger compared to the direct link. So this 5.1, 5.2, this correspond to the average channel gain of the direct link. So in this case, if one sees, particularly like if I look into the stability region, SIC kind of gives very bad performance. That is kind of expected because hexagon, if I look into, I've not gone into infinite block length results, but in general, we know that SIC and kind of scheme does well at the very high interference region. So in this case, one can see that SIC gives stability region is kind of very small compared to the other two cases. But what is interesting is when I look into the joint decoding still gives a very good stability region, even if the interfering link is not very strong. That is something interesting to observe. The joint decoding performs well, even though the interference link is not very strong. And as I increase the interference channel gain to 1.5, then one can see that basically joint decoding is kind of doing much better compared to TIN or SIC. So in this case, one can see like what is happening in terms of stability region, but what is also important to see what is happening in terms of latency. So then only we may be able to decide which scheme may be good. And so that is what I am showing in my next plot. So what is plotted is, in this case, I am showing only the results for the case when the interfering link is kind of weaker compared to the direct link. So the first plot corresponds to the stability region, whereas the second plot is basically corresponding to the delay, whereas the plot in the bottom corresponding to the average age of information. So in this case also what I'm plotting is delay and the average age of information only at receiver 1. Receiver 2 we are not kind of plotting because there is no interference on it. So that is why we are not showing that part. The more interesting part is when there is interference. Now in this case, what one can see is basically like this lambda 1 and when lambda 2 is basically high, as we expect, this delay are increasing in case of SIC. And that is what also one can see, like in this case, okay. So there is one more parameter that I did not mention is this K and N. So what we have seen is actually whatever rate I am choosing, that is also kind of very important. And that may give rise to some of the other interesting optimization problem that we have not considered in this work. Like for example, how much information bits I need to optimally encode in a packet. So particularly in this case, this K1 and K2, I have chosen to be same, but it doesn't require to be same. It can be different. It doesn't have to be same. It can be different. So in this case, the rate is around 0.1. So basically what I'm aiming for a scenario where the data rate is kind of very low, but I'm using kind of a large packet to encode my data. So in that case, what we see is that the stability region, if I see, it's kind of very large. But what is happening to the delay now when the number are very high, delay is going to be very high. But now if I look in terms of age of information, so there again, what I see is when lambda 1 and kind of lambda 2 is high, particularly SIC performance is not very good, but joint and TIN still gives a good performance. But when lambda 1 is kind of low, or lambda 2 is kind of high, or lambda 2 is low, then you can see that the AY kind of again increases. So ideally, I like delay to be as small as possible, age of information also to be small possible. Now in this case, I have kept R to be 0.1, but let's see what is happening if I increase the rate. So now what I've done is I've increased the rate and then try to see what is happening. So now this is the parameter, that is what I'm playing at the physical level, then trying to see what is happening, how it is affecting some of the performance metric at the network level. And now what I see is like, in this case, I'm not changed any other parameter, they're all same. Now what one can see, the stability region has kind of surface change. That one now it's kind of changed. Now the stability region has shrink. And then also I can see that like the effect of the delay, whatever I'm having, that is kind of shooting up for the SIC. But interesting thing is still like the TIN scheme and the joint decoding scheme, they are still giving good performance, or even it may not be very easy to see from this plot because we have kind of rotated it and seen from the simulation that I've not done shown here. One can see actually that joint decoding gives the much better performance. So, but the problem is like you may have to always ensure that when you are doing this plot, we are always operating in the within the stability region. We should not go beyond it. And then when you're plotting the edge of information, again, you can see like when I'm having a higher arrival rate, SIC is kind of doing very bad. Whereas TIN and joint, they are doing good. And in this case, one can see like joint particularly again doing better even compared to TIN. So characterizing it is exactly is not easy because of the complexity of the expression. But what we observed is that particularly some of the low rates as well as some of the cases high rates scenario, even when the interference is not very strong, and then joint decoding gives a better performance compared to TIN as well as SIC, provided complexity is not a concern. And when we improve, I have not shown the results when this interfering link is kind of stronger. So that result I have not shown. If we improve, if you go on increasing the interference strength, then joint decoding kind of does better. There are some other results I have not shown here, where even for the high interference regime, treating interference as noise does better compared to SIC. That is something was surprising to us, but I have not shown it here. And with this, I am almost coming to the end of my talk. I hope I'm not exceeding the time. Some of these things I could not discuss today. To summarize quickly, like basically I presented the stability region for the G interference channel. The results can be extended for the interference channel, but we have to use the stochastic dominance technique. Many of the expressions that we have derived the probability of successful decoding, they are actually applicable even for the two-region interference channel. Maybe some slight modification we need to do, but they are kind of applicable. There are a lot of scope, I feel. Currently, like I have assumed kind of fixed rate transmission, and but how do I adopt my rate? If I want to adopt my rate based on channel condition or maybe limited channel condition, so that is kind of some other work we are focusing, but that doesn't involve this cross layer. And also I have told like particularly if one look into all these plots, there is a lot of things one can do from optimization aspect, and no doubt there is a lot of work need to be done in the context of finite block length information theory that I have not mentioned here. There are some other research work I have not kind of just thought of mentioning few, like as I was working on information theoretic secrecy during my PhD, I still keep on working on some of these pure information theoretic problems. And also we are looking into some secure communication in presence of active eavesdropper. And no doubt, like some of the works that I'm presenting, it's only because of my student efforts. So I like to thank them. And with this, I kind of conclude my talk. Yeah.
Thank you, Professor Parthajit, for an informative talk. We can take few questions and then close.
Yeah, I'll go first. Parthajit, what if there is feedback and cooperation between the transmitters or receivers?
Yeah, so currently, yeah, so I think these are very important questions. But some of the problem I think we can able to do. But one problem that will come fundamental in nature is coming up new achievable results in finite block length information theory itself. So that is where I feel some of the bottlenecks are there. But some of the trivial results one can try to do and try to do for like cooperation and other thing. But one of the concern will come is how good is this finite block length results? Yeah.
Okay, thanks. Also, in your finite block length analysis, did you have to do any modification to the finite block length analysis itself because your interference is also a finite block length interference?
Yeah. So currently, like what we have done is we have not derived new finite block length results, but we have seen some of the works where for the multi-user scenario, results being considered with finite block length, and they use non-Gaussian results, but they are not fully appropriate. And so that is where like we have been very careful so that we don't cause a non-Gaussian interference. There are one or two results exist only in Gaussian interference channel, which kind of do this kind of non-Gaussian interference, but it's only applicable for high interference region. But currently we have not done any kind of finite block length results in this work because our objective was a bit different here.
Okay, thank you.
Yeah. So
I had a question regarding the short packet communication aspect. So maybe I missed it the way you explained it. So what makes this analysis suitable only for short packet communication as against, say, a bulk transfer from the modeling perspective?
So currently, like now if I look into the literature, particularly information theory, there are two kind of literature. One is like which focus on this Shannon kind of developing results, and which has the underlying assumption that the code word length has to go to very large or has to go to infinite. But once I have this short packet communication, I cannot use all these existing results which are existing in the network information theory. So when I'm trying to particularly look into this short packet communication, I am trying to take the length of the packet into account. Like for example, like I think I have one expression somewhere. So in this case, if you see this error expression, this n basically captures the length of the packet.
So this is mainly from the information theory
Yes.
context.
Yeah.
Because I was wondering, like from the network side, because since you said combined network and lower layer, so there the context also becomes that you have multiple sources which are having some stochastic arrivals, which are again like very kind of erratic arrival processes.
Yes.
So that this model doesn't really capture.
I agree on that. Actually, there are some works which actually, I think what is more going to be important is if one look into this particularly uRLLC and this kind of thing, some of the things I think what it doesn't take into account is what is happening in the tail probability. So some of these uncertain events are there, they may suddenly appear. How do you take care of that? So currently, I think these things are important to take care. So currently, this result doesn't take into account. I think that is what you may be trying to mention.
Yes,
yeah.
Thank you.
Yeah. It's only try to capture the random activity of the, random arrival of data at the users.
Thank you, Professor Parthajit. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The link to the slides will be posted on the webpage. Thank you and have a great day.
Yeah, thank you. Bye.